So, let's see. If I mention the short story by Leo Tolstoy, How Much Land Does a Man Require? How many people have read that? Okay, that is not a prerequisite for this class. However, maybe here's another good question. How many people know about the Gutenberg project? Good. And I'll tell all of you about it. Things written before copyright law became quite so broken are in the public domain. And the Gutenberg project is a project which serves to collect those things together. In particular, a bunch of the works of Leo Tolstoy are in the public domain. You can find them on this site. In particular, I suggest, not because of mathematical content or anything, go and find the short story, How Much Man Does a Land Require? So, here, I'll give you the TLDR of the story. The premise of the story is a Russian man named Paco lives in poverty and says to the devil, "Devil, I will sell you my soul in exchange for lots of land and possessions." Devil says, "Great." Paco goes through his life, acquires land and possessions, and gets greedy. He comes across a group of people who have a very interesting trade system set up. If you give them a bunch of money, they will let you walk around a chunk of land, digging holes for posts from herbivores. And if you manage to enclose a region of land and come back to where you started, all of that land is yours. If, however, you don't make it back, they keep your money and you don't get anything. So he says, "Great, I'll do that." So he starts out on his way, digging holes as he goes. He makes lots of coverage. He notices then that the sun is setting. This deal ends at sunset. So he then starts running in a big hurry to get back to the starting point to get his land. He makes it back to the starting point at the end and then promptly dies of exhaustion. It is a Russian short story, so you don't expect a happy ending. And the closing line in the story is, and so we discover how much land the land requires is actually about 6'5", 3 foot. Just dark. Anyway, there are really good things to talk about in terms of ethics and lifestyle. It's a good piece of literature, but I don't want to discuss those questions. This is a math class. Let's not ask how much land a man requires. Let's ask how much land this man could acquire without dying. So, by training, let's make some suppositions. Let us suppose that Paco discovers that even with the constraint of having to stop and dig holes occasionally, he can cover 40 miles in a day, sundown to sunup. That may be unreasonable, but that's okay. The actual number doesn't matter. Let's also, to make something simpler, add the assumption that he must acquire his land in a rectangular region. He has to go east some distance, north some distance, west some distance, south some distance, get back to where he started. So, with those constraints, let us try to discover how much land he could acquire. So let's just unravel everything. He's going to cover 40 miles distance walking in a rectangle, so what's the perimeter of that rectangle? 40 miles? So let's see, 40 miles, maybe we'll draw a picture. There's this rectangle. He'll walk some distance east, some distance north, and then he'll go back. Using that rectangle, what's the formula for its perimeter? How far do you walk? I guess you can count it up. You go x plus y plus x plus y. Well, how much? 2xy? No, I said something totally wrong. 2x plus 2y, right? So, if he's going to cover a 40-mile rectangle, we have this equation that governs how x and y behave. Do you think you could take that and solve it for either x or y? Which would you rather solve for? Probably doesn't matter, it looks pretty symmetric. I guess let's solve for y. What do you get for y? You guys are just being really quiet, and it's hard for me to judge if you guys are feeling non-challenged or stuck. Do people want me to go through the algebra? Okay, I see at least one head doing something that looks like nodding. So let's do it. 40 equals 2x plus 2y. I want to solve it for y, so let's get everything not y onto the other side. Oh, shoot. So 40 minus 2x equals 2y. So what should you then do to get y on its own? Divide by 2. So that'll be 40 minus 2x over 2 equals y, but one should simplify. I see a 2 in the denominator. Is everything in the numerator even? So we can take a 2 out of everything in the numerator and cancel. So it looks like y is equal to 20 minus x. That help? Good. What's the area of a rectangle of base x and height y? Base times height, x times y. So the area, which is the thing we want to maximize, we want to make the area as big as possible, is equal to x times y. Do I have a formula for what y is? Yeah. That. So it's the same thing as x multiplied by 20 minus x, also known as 20x minus x squared, or maybe just for the sake of writing our quadratics in decreasing order, I write it as negative x squared minus 20x. Cool, so here's the thing. Now we have a function that models area. Area is the thing that we want to maximize. So if we can determine what value for x maximizes that area, and then maximize that area, well, we'll have solved Pacom's problem, right? We'll have determined exactly how much area he can probably get. So let's do that. Oops. Nice. So I've written on the board for convenience the completing the square formula. Or we could follow through the steps of completing the square. Which would people rather do? How many people would just want to appeal to the formula? How many people want to go through the method of completing the square real quick? Cool, let's do that. So on the one hand, we'll be able to know exactly what we should get. So let's complete the square. So that means I need to take negative x squared plus 20x. I would like to write that as, well, I just remember that this negative is going to be out front. Negative x plus or minus something squared, and then there will be some error term. And maybe we'll try to just like flip together a different plan. So if you just write out what a perfect square is, x, well, keep the negative sign, x plus or minus b squared. That'll be negative x squared minus or plus. Let's absorb the plus into the b. Plus 2bx plus b squared. So that'll be negative x squared minus 2bx minus b squared. So I need the thing in front of the x to be 20. So what seems like a good choice to make for b? What choice of b will result in that number being exactly 20? So we'll have negative x squared. No, I guess it's negative. So minus 10 squared, and now there will be some error term. And in order to figure out what the error term is, let's now forget about what we just did and just think about expanding this out. If you want to expand this out, what would the constant term wind up being? What would be like negative 10 times negative 10? So negative 100. So that right now has constant term negative 100. On the left-hand side, what is its constant term? 0. So we're off by 100. So we can add 100. And there's a way to kind of think through the method of completing the square. On the other hand, let's run through this. If we use the completing the square formula, we'll get a equals negative 10, b equals 20, c equals 0. And so we can appeal to this. We'll get negative for a, x plus b over 2a, x plus 20 over negative 2 for 2a squared minus b squared over 4a minus 20 squared over 4 times negative 1 plus c. If you go and expand that out, do you get exactly what we have above? Should which be a negative?
4 times negative 10. No, not there. Yeah.
Oh. No, that should have been a negative 1.
Oh.
Yeah, right, the a was just a negative sign. Yeah, that's my fault. Otherwise, people happy enough? Cool. So, now that we have this thing in the form of having completed the square, is this easy to graph? Yeah, so if you wanted to get its graph, I want to draw the intermediate steps. You would start with the graph of y equals x squared, and what's the first thing you would do? Here, a shift to the right, then up, then did you reverse? So you've made one mistake in your order of things. You should deal with the negative sign out front faster. So try again. Start with graph of y equals x squared. Flip. Next I should shift right. Next I should shift. So I'll see this point shifted right by 10, up by 100, and I'll see a downward curving parabola. Looking something like that. And I was careful about where those x-intercepts are, but do we care about the x-intercepts in this problem? If we want to maximize, are the x-intercepts relevant? No, we just want to maximize. Looking at that graph, what is the maximum value you see? 100 is the maximum value. Right? Max value should be the output. What x produces that maximum value? 10. So that tells us everything. I guess we have to put everything back in terms of context. In particular, let's put all the units back. So x, what did x mean in this question? Was the length of the rectangle in miles, I guess. So our Pockum's ideal rectangle had a length of 10 miles. Height is probably not the right thing to call it, but could you determine the other side of the rectangle out of that? Yeah. Do we have a formula for y in terms of x? Y is 20 minus x. Right there. So the height will be 20 minus 10, also known as 10 miles. And what is the area of this rectangle then? 100 in what unit? So, what's the takeaway? If Paco wants to acquire as much area as possible without dying this time, he should capture his land in the shape of a 10 by 10 rectangle, also known, I guess, as a square, and he can get 100 square miles for whatever price it is that he pays. How do people feel about that? That procedure seem pretty okay? I want to just formalize a few things now, so the next page I'll wax just a little bit abstract, and then we'll go back into some applications. In particular, we use the completing the square formula on that side. So the completing the square formula tells us that if we want to graph ax squared plus bx plus c, we can instead graph a times x minus b over 2a squared plus c minus b squared over 4a. Only I want to go through the procedure. We have a formula. So just look at that formula. That's a thing that's easy to graph. So let's just picture it. So first let's deal with the case that A is positive. In the case that A is positive, we'll start with the standard parabola. We'll stretch it by a factor of A. Still upward opening, or has it become downward opening? Still opens on the upward side. Then we'll shift it, and we'll shift it. Is it still upward opening? So it will be in the case that A is positive, the graph of the parabola will open upwards. When A is negative, this parabola will open downwards. And we can even sketch a picture. Let's just decide how far we shift. It looks like we shift b over 2a to the right. So we wind up over here with an x value of, oh, that's wrong, b over 2a, and a y value of c minus b squared over 4a. It will open upwards. So by looking at that picture, does that graph have a global maximum or a global minimum? Has a global minimum. And what x value produces that minimum? Oh, son of a diddly. Negative b over 2a. Since I screwed up when I typeset the thing, I put a minus sign when I meant to have a plus sign.
Why would it be a minus?
Why would it be a minus? Well, if instead my parabola looked like that, it would be, right? So I also just make lots of typos. When A is bigger than 0, when A is less than 0, it'll be a similar shift. First we'll shift left by b over 2a, then we'll shift up by c minus b squared over 4a. We'll wind up wherever it is that we wind up. And then will the parabola open upwards or downwards? I'm sorry. So I'll wind up with the vortex at the exact same point because we do the same shifting either way. But will the parabola open up or down? Does that have a max or a min? And has a maximum at the exact same x value, x equal to negative b over 2a. So here's the main technical result of today. If you see any quadratic function, ax squared plus bx plus c, then the graph of that function will have a parabola, be a parabola with vortex at negative b over 2a, as its x value. We could also write down the y value. Maybe I'll say for a moment why I wouldn't remember the y value. When a happens to be bigger than 0, the vortex minimizes. When a is less than 0, the vortex maximizes. What about when a is equal to 0? What can you tell me about the vortex then? What type of function is ax squared plus bx plus c when a is 0? Well, then it's actually secretly a linear function. So its graph is a line. Is there a vortex at all? You shouldn't use that technique. It's a line. Similarly, if you don't like remembering formulas, but I think that as far as a vortex formula is not so hard to just internalize. The vortex of the parabola ax squared plus bx plus c is negative x equal to negative b over 2a. If you don't like remembering that, then you can remember how to complete the square. And then you just need to remember how you've shifted it. So you'll notice that I've also written down the y-coordinate of the vortex, because I could. But that's like slightly complicated looking by comparison. If you know the x value of the vortex, how could you recover the y value? Yeah, just say it loud enough.
Me?
Yeah.
Plug it back in the points.
Yeah, you know the x value. You have a formula for the function. Use that formula to find the y value. Don't worry about this when you want to see the y value. So that's as technical as I'm going to get today. Just this. If you have a parabola, the coefficient a tells you whether it opens up or opens down, so it tells you whether the vortex maximizes or minimizes. If you want to find the x value that produces the global max or global min, find the vortex. The vortex is at x equal to negative b over 2a. So I'm going to want some amount of permanence. I'll just remember that. So let's make some more attempts. So the remainder of this packet is just a couple more examples. So the first is another area optimization. Next we see at what point is a human cannonball at her maximum height. And finally, we have an economics example. If you have a financial model, can you use it? And I think there's enough time to go through the lot of them. So let's just start talking through it. Let's do a geometry one first. Here's the premise. You have a sequence which you want to vary in the desert. So you are going to acquire, or maybe you aren't actually acquiring, maybe you're just going to build some fencing on public land and hope no one notices. So you said you're going to fence off an area. This region you're going to use has a cliff along it, so you're just going to use the cliff wall as one of your walls in order to save you some money. You're going to assume no one's going to climb that cliff, or possibly descend the cliff. I just guess I didn't specify if you're at the top or bottom. So you're going to fence off a rectangular area, like so. Somewhere in there you will hide whatever it is that you want to keep people from seeing. If you have a budget for 1,000 feet of fencing, let us try to determine how much area we can capture. And you'll notice in the first problem we wound up with a square being the optimal shape. What do you think? Will a square continue to be the optimal shape in this problem? How many people would want the answer to be yes? How many people would want the answer to be no? Okay, well, we'll see. If it does turn out to be a square, then you just want the square whose perimeter is 1,000, and that would do the job. But we'll see if that actually is it. So here's a picture. So first let's try to unravel things. I told you you have a budget for 1,000 feet of fencing. And there's the shape that you're going to fence off. It looks like I can pick two parameters, how far to the east of the cliff I go, and how far north-south I have the fence run. What would you like to call those? I mean, I just need some variable names. What would you like to call those?
A and B.
Great. Not all variable names need to be inspired. So I guess that means this distance will also be A. So, if I build that fence, then in terms of the variables A and B, how much fencing have I used? I guess I've used A feet, B feet, and then A feet again for a total of Does that look like you could solve that for either A or B? Which would you rather solve for? B looks easier, I guess. So we want to maximize area in this problem. What is the area of that rectangle? Just A times B. It's length times height. Do I have a formula for B in terms of A? So let's use that. I get A times B, that's A times 1,000 minus 2A with parentheses as such. That's 1,000 A minus 2A squared equals negative 2A squared plus 1,000. Oh, maybe A was a poor choice of variable names just for me because A is supposed to be like a coefficient in there. That's okay. Can we use the vortex font? So let's ask some questions about the vortex. I'll shift that up. So there's a degree 2 polynomial. So I know its graph will be a parabola. Will it be upward opening or downward opening? Downward opening. So will the vortex maximize or minimize? Maximize. And that's important to check. If you don't check that, then you run the risk of accidentally minimizing when you're meant to maximize. So instead of finding the best possible answer, you'll have found the worst possible answer. But A is, well, the coefficient in front of A squared is negative, so it maximizes. So according to the vortex formula, so here it's awkward, the independent variable is called A instead of X. So by the vortex formula, A is the coefficient in front of the linear term, negative the coefficient in front of the linear term divided by 2 times the coefficient in front of the square term. So let's just substitute that in. What's the coefficient in front of the linear term there? There. What's the coefficient in front of the linear term? 1,000. So I'll see negative 1,000 divided by 2 multiplied by, what's the coefficient in front of A squared? What is that? So that tells me one important thing. That tells me if I want to maximize this area, I should take A equal to 250. So that's how far east to go. Can I use the information given to determine, oh yeah, thank you. Can I use the information given to determine what B is? Yeah, I probably have B written down in terms of A somewhere on the page. So take that A value, what do you get for B? Well, I guess alternately you could like go back to the original thing. The perimeter needs to be 1,000. I've taken up 250 on the top and bottom, that leaves me with 500 feet left. Oh, I guess units are important. B is 500 feet. That's how far north. And we're interested in maximizing the area. What is the area of this rectangle? Say it louder.
1,000.
I think it's bigger than that.
25,000.
Yeah, so that's the amount of fencing that I've used. So the area is going to be the product. So let's see, 3 zeros and then 5 times 25. 125K? In square feet, that's a really big number. So I think if you wanted to actually do this and report the answer in a way that would give you a sense for how big it is, you might want to convert that to something like square miles. I won't, but you would want to, I think. On things like the homework, I certainly would not want you to switch to square miles. How do people feel about that problem? That go okay? Yeah, so in this one, we set up a problem from the geometry, and then we optimized it. The next two problems, we won't have to do the fourth step. So here's one setup. Rosa Matilda Richter, under the stage name Zazzle, is the first recorded human cannonball. She walked in England in the 1870s. So in what follows, I haven't pulled any of these numbers from any of reality. I think that's much too fast. If Zazzle is shot up into the air with an initial velocity of 80 meters per second from the ground, and then later lands safely in a net, then physics predicts her height after any amount of time t as negative 5t squared plus 80t. Out of that information, can you determine the time at which Zazzle acquires her maximum height? I think so. And maybe I'll give you guys a choice here. I can just shut up for a second and you can figure it out. Or I can keep talking. People want me to keep talking? Okay, I'll keep talking. Presumably this is going to be another application of the vortex formula. If you just read that polynomial, is this graph a parabola that opens up or opens down? Down. The coefficient in front of t squared is negative. So this opens downward. So does the vortex maximize or minimize? If you read the problem, are we interested in maximizing? So that's good. That means we just need to find the vortex. We have a vortex formula. So the vortex is at t equal to negative b over 2a. This time I can safely use the variable names b and a because they're not otherwise appearing in the problem. Let's read them off. What is b? It's the coefficient in front of t, so it's 80. So I intentionally wrote these coefficients in the wrong order in order to emphasize that it doesn't matter what order you are presented coefficients in. Right? Addition is commutative. But if you are convinced that you're likely to screw that up if they're in the wrong order, then put them in the right order. So b is 80. So I'll see negative 80 over 2 times what is A? And what is that? Yeah, for some value of it, 8. Yeah, the denominator is -10. So the total is 8. And that's a time value. What was time measured in this question?
Seconds.
Seconds. So Zazzle acquires her maximum height 8 seconds after being fired out of the cannon. How can we determine her height at that point? Plug it in. We have a time value to use. So the maximum height is equal to the height at 8 seconds. So that's 80 times 8 minus 5 times 8 squared. That seem reasonable? And maybe in order to emphasize that I've rigged this so that the numbers work out well, even though it looks like the numbers are all really, really big. I see an 8 squared in the second term. In the first term, do you think you could pull out an 8 squared? Yeah, because 80 is 10 times 8. So let's pull that out. That'll give me 8 squared. This piece will now be reduced to 10 minus 5. So far, so good? And what are the units? What is height being measured in? Very good. That problem makes sense? So we have time to do one last one. And so I'll give you guys 2 choices here. I have it listed as an exit quiz, and I have 5 minutes left. So either I can talk through this one if you want to see me talk through one more example, or I can have you guys talk through it as soon as you present to me a correct answer to the question. You're free to go. How many people want me to keep talking? Okay, not an exit quiz then. You will be here for the full time. So let's try to do this. So here's the setup. So the revenue gained by a sale of needs, which if you don't know are a thing which everyone needs, is modeled by the function revenue in terms of price. So P is the sales price of a single need. The revenue gained by the sale of needs is given by -1/2 the square of the price plus 1900 times price. So, given that information, if the once more wants to maximize revenue, R, how should the once more set the sale price of a single need? There's a question. So let's proceed in the same way. So do we want to maximize or minimize? Maximize, okay. If you want to imagine the graph of that function with P being the independent variable, R being the dependent variable, you'll see a parabola, upward opening or downward? Downward, because -1/2 is negative. So will the vortex maximize or minimize? Maximize. So we just need to find the vortex. So let's use the vortex formula. So the vortex formula tells that the price where we should set it to acquire the maximum revenue is price equal to -b over 2a. What is b? 1900. So I'll see a negative, we'll just carry that along. Divided by 2 times what is a? That was very fast, but did people follow how I just matched up symbols? Okay. What is that? Are there any units specified in the problem? It's possible that maybe the problem is intended to be walked in USD. However, given that this is pulled from the lifting of the law acts by Dr. Seuss, and I don't think Dr. Seuss specified a currency, I think that's the best I can do. Cool. How do people feel about optimization of quadratics? Yeah, once you get down to a quadratic model and you know what you want to do with it, the vortex formula just does it. You have to do some computation for it, but that's not that bad. Sometimes you actually have to set up a model from a geometric situation, and out of that, you can maximize the. Cool. So, I guess maybe I lied. We are getting a little bit early. I'll be here until everyone's gone. If you want to ask me any questions. I collected homework, right? Yeah. Okay, good. And I guess if you want to ask me questions about the homework, I don't have much time. I have a meeting at 11, but if it's a very short question, I might be able to answer it. And again, if you lost points because you didn't do that one PDF problem, do it, and then come by my office at some point, maybe during office hours.
You said you had a stick.
Oh,
Yeah. It'll be upstairs, so just
Feels like a
head up when I can.
What?
Oh, fantastic, thank you.
Where's your room?
Fifth floor?
That's not good. It's really
5:33.
weird. She's never done that before.
But I mean, there's not no reason for you to get there before
But
the door will be shut. Are you in a hurry to get to your next class or something?
Class.